Welcome everyone to today's session in physics, that is electric field lines. A very important topic in that chapter from which we can expect 1 mark, 2 mark questions for board exam. So let's move on to the topic electric field lines. So as the name suggests, electric field lines. Electric field lines means it is the pictorial representation of electric field. So electric field lines will be representing an electric field both in magnitude and direction. That means we can make conclusions about the magnitude and direction from the electric field lines. That's what electric field lines are. So actually what we mean by electric field lines are the curves that means they are the curves which represent the electric field, or if you have an electric field, suppose this curve represents a field line. If you want to find the direction of electric field at any point, you have to draw the tangent at that point. The tangent to the curve at that point gives the direction of electric field at that particular point. If you want to find the direction of electric field at any other point, similarly you draw the tangent. That tangent will give you the direction of electric field. So that's how electric field lines are defined. That means they are the curves, the tangent to which at any point gives the direction of electric field at that point. Okay, so that's what we mean by electric field lines. Actually, they are the path moved by a positive charge. If you keep a positive charge at this point, okay, small test charge. If you keep a small test charge, small positive test charge here, the direction or path followed by that positive charge will be along this field line. So field line is defined in that way also. Electric field line can be defined as the path followed by a small positive test charge placed in an electric field. In an electric field, when a small positive test charge is placed, what is the direction or what is the path followed by that small test charge, positive test charge? That is actually the field line. So in both the ways we can define field line. One way, as I said, it is the curve, the tangent to which at any point gives the direction of electric field at that point. In the second way, it is the path followed by a small positive test charge kept in the electric field. So in both the ways we can define electric field line. Okay, now it's not compulsory that you have to draw only one line. As many lines as possible you can draw to represent an electric field. So there can be many electric field lines which represents an electric field. Okay, and the number of electric field lines. So suppose you have many electric field lines like this. And you have some other electric field. So this represents an electric field E1, and you have some other electric field like this represented by the same number of field lines. This is E2. So two electric fields E1 and E2 represented by two sets of field lines. The number of field lines are same, but we say E1 is stronger. E1 is stronger than E2. Which one is stronger? E1 is stronger. So what makes the distinction between a strong field and a weak field in terms of field lines? The closeness, the relative closeness of field lines gives us an idea about strength of the electric field. So if the field lines are very close to each other, it means or it represents a strong field, and if the field lines are widely separated, if they are far apart, that set of field lines represents a weak field. So relative closeness of field lines, it is a measure of strength of the electric field. If they are close to each other, closer electric field lines represent stronger field. If they are far apart, it represents a weak field. So this is how we conclude about the magnitude and direction of electric field given by a set of electric field lines. So arrow mark shows the direction of electric field. So at any point you can draw the tangent. That tangent will give you the direction of electric field, and magnitude, strength, that we conclude or compare by this way. That means looking at the relative closeness of field lines. So it is not the number of field lines actually that is important. There can be any number of electric field lines, but the number of electric field lines per unit area we can say. That means, as we said here, the relative closeness, that is a measure of strength of electric field. So this is about the field lines. Now we will discuss how the field lines of different point charges, two charge systems, etc. are. Now first, field due to a positive charge. So field line, it shows the direction of force a positive charge would experience when we keep it in that field. So the thing is this, in the case of an isolated positive charge, the field lines are directed outwards. That means it will represent the field lines, or the field lines are directed radially outward. So in the case of positive charge, the field lines are directed radially outwards. Now in the case of negative charge, the field lines are directed radially inward. That means towards the negative charge. So field lines are directed towards the negative charge in the case of negative charge, and in the case of positive charge, it is directed outward. Now the spacing between the lines indicate the strength of the electric field. A stronger field would have more closely spaced lines, and weaker field will have less number of field lines, or widely separated field lines. So this is about the field lines due to point charges. So the thing is this, in the case of positive charge and negative charge, we can say the electric field lines, they start or end at infinity. In that way also we used to say. That means the field lines, they start or end at infinity. It means that in the case of positive charge, the field lines, they start at the positive charge and end at infinity. And in the case of negative charge, the field lines, they start at infinity and end at the charge. So this is a common what characteristic we say about the field lines due to positive and negative charge. The field lines of positive and negative charge can start or end at infinity. They start from infinity in the case of negative charge, and they end at infinity in the case of positive charge. Now, the electric field lines due to two charges, which are unlike charges, that means positive and negative, and they are of equal magnitude. So in the case of two charges, unlike charges, the field lines, they start at the positive charge and end at negative charge. So field lines, they start at positive charge and end at negative charge, and you have the field lines shown as given. Okay, so this is the field lines due to two unlike charges of equal magnitude. And this diagram shows the field lines due to unlike charges itself, but they are not of same magnitude. So we can compare and contrast. That means in the previous case, the number of field lines drawn were same because both the charges were of equal magnitude. In this diagram, both the charges are of different magnitude. So the charge with the larger magnitude will have more field lines, or more closely drawn field lines there. So it shows that the field due to that charge is more stronger compared to the field due to the other charge. Okay, so this also two charge system. Now this diagram shows the electric field lines due to two charge system itself, but it is like charge system, two like charges. So as we know, like charges repel each other. So these like charges, they show repulsion. The field lines also show repulsion. So these are the field line representation of two like charge system. Now this shows a uniform electric field. So uniform electric field, it is written, it is between two parallel metal plates, and what I would like to convey is always a uniform electric field. The word uniform electric field means an electric field which is having constant magnitude and same direction throughout the space wherever it is applied. So in the space where it is applied, the uniform electric field will have same magnitude and direction. That's what we mean by uniform electric field. So a uniform electric field is represented by a set of field lines which are equidistant and parallel to each other. That point is very important. Equidistant parallel field lines represents a uniform electric field. So this given diagram represents a uniform electric field, and it is produced by, or it is the electric field between two parallel metal plates. Such things we'll be discussing later. Field between two charged plates and all. So this field is what I would like to convey now is this field is uniform electric field. Uniform electric field means of constant magnitude and same direction. Now this represents field lines in the case of a system. This system consists of a point charge, and at a distance you have a charged plate. A point charge, it is positive charge, and the other charged plate, it is a negatively charged plate. So there will be attraction as we know, but the field lines, how the field lines will be? Field lines will be curved like this, because on the surface of the metallic plate, the field line should be normal. It should be normal, and so the field lines, when they strike or when they reach the metallic plate, the field line should be normal, and that angle will be 90 degree. Like that we have to draw. More about this angle 90 degree we will be discussing in coming days or coming sessions we will be discussing. So for time being, learn this diagram. So all these field lines diagrams very important for the exam. You have to learn. It's given in the textbook also. Learn properly. Now we discuss more on electric field lines, the properties of electric field lines. Okay, so as we said, in the case of positive charge and negative charge, the field can start or end at infinity. So that point you can emphasize. Field lines start from positive charge and end at negative charge. And if there is a single charge, they may start or end at infinity. And second property, in charge-free region, electric field lines can be taken to be continuous curves without any break. So in charge-free region, the electric field lines are continuous curves. So there is no break in the case of field lines. Then the third one, very important point, that is two field lines can never cross each other. Two field lines can never cross each other. So if they did so, at the point of intersection, you know, when we draw the tangent, if the two field lines cross each other, if at the point of intersection, there can be two tangents which shows two directions for the positive charge to move, which is not possible. So two field lines can never cross each other, and that is a point which can come as a 1 mark question. They may ask two field lines can never cross each other. Why? Like that question may come. So how will you write answer? That is, the answer is this, that is, if the field lines, they intersect each other at the point of intersection, there are two directions possible which cannot be, which is observed. Okay, so that cannot be. Then the fourth point, electric field lines do not form any closed loop. That point also is very important. That is, we said they start from positive charge and end at negative charge. Never it will start from negative charge and end at positive charge. So they are not forming any closed loop. They start at positive charge and end at negative charge. They will not form any closed loop. So these 4 points are the additional points. The other points we already mentioned. What are field lines? The tangent to the field lines at any point gives the direction of electric field, and the relative closeness of field lines shows the strength of the electric field. Then the additional points what be, and the diagrams also very important. This shows the field lines due to two charge system, that is unlike charges, and this is the field lines due to like charges. This is the case with a negative charge and this is the case with positive charge. All the diagrams very, very important. Hope you followed. With this we conclude. Thank you.